sorry to disappoint you. There was another more interesting title for the talk, but that's the real subject, you know. So, of course, thank you for the invitation. It's an honor to be here. Very glad. And I hope to make a talk same level, is close to the level of the talks I have been attending to. Okay. So, the subject is the classification of flows and Stein surfaces, holomorphic flows. So, actually, what I had in my mind when I started this is, the Marcos-Yamaha conjecture for real flows. And you have a vector field in R2, then it's infinite. Real vector field in R2, it's infinite one. So there is this work by Gutierrez and other people. They prove that if you ask that on each point, the spectrum, which means the eigenvalues of the derivative of the vector field, have this real negative part, then you prove that there is a point, a singularity, which is a global attractor for the vector field. So the dynamics, after all, is very, very understandable. So I was asking myself, if you consider a complex vector field on C2, can you somehow prove the existence of a singular point, which somehow is going to be an attractor for the dynamics of the vector field? And somehow can you linearize it globally? What happens in the real case, at least topologically, So the answer is somehow yes, if you assume that the vector field is complete. So actually what we do is the pairs, where n is a Stein surface, and X is a complete holomorphic vector field with isolated singularities on n. So it's complete. Means the holomorphic flow is defined by every complex time. So what we prove, that's the result. We make some topological hypothesis on the Stein surface. Then we prove that the manifold is holomorphic to C2 if it's equipped with a holomorphic complete vector field that has a finite number of singularities. And you suppose that there is one singularity, which is the critical singularity, non-degenerated linear part. There are many generalizations. Actually, you don't need to suppose that the linear part is like that. But in this talk, to make the ideas more clear, we assume that we have a holomorphic vector field, complete one, on a Stein manifold. Suppose the guy has a critical singularity. That way, the linear part like that. Then, the manifold is holomorphic to C2, and the vector field is globally linearizable. This means that there is a holomorphic map from the manifold to C2, taking the vector field into that linear guy there. Okay. So that's the result. Okay. It's a global linearization theorem for holomorphic vector field if the guy on a Stein manifold surface, if it has a critical singularity, that non-degenerate that way. Not happening. Thank you. So the converse is clearly true. If a linear vector field like that, is the critical. So the idea is to use some results from Masakazu Suzuki from the middle 70s on holomorphic flows, on parabolic foliations on Stein surfaces. So a fundamental contribution was given by this Japanese mathematician who introduced the potential theory in this word. So let's remind some of his results. So we have C action. C action is just a holomorphic flow. On a normal Stein analytic space, so it does everything on a more general setting of dimension n greater than at least 2. So this first thing says that there is a generic orbit. This means, well, the orbits of holomorphic flow, we know that they are either C or cylinders, no, C star, or complex toric, no? So, since we are dealing with a Stein space, we don't have compact curves there, so the orbits are either C or C star, cylinder, no? C minus 1 point. So these two orbits, they don't exist together in an abundant way. Suzuki proves that if you take out an exceptional set, where exception means zero transverse logarithmic capacity, then all orbits are of the same type. So you have generic orbit, which is either C or C star. Okay? The orbits C star we are going to call periodic orbits. So he also proves that when you have a flow, any orbit of type C star is closed of the orbit of the singularities. So actually, if you put the singularities using Hermann-Stein theory, each orbit C star is contained in an analytic curve. So the periodic orbits, like in the real case, they are closed. This is for a flow on a Stein space. Okay? So in dimension 2, Suzuki's result says that if the generic orbit is periodic, then you have an homomorphic first integral. This is a corollary of a much powerful theorem that he has about parabolic foliations. Anyway, for us it's enough to say that if the generic orbit of a holomorphic flow on a Stein space is periodic, then you have a homomorphic first integral in the whole Stein space. Okay. So we're going to use these to prove our global linearization theory. So in what follows, we have just to fix the ideas, we have our Stein surface. It's not a normal analytic space, it's a real surface. And X is a complete holomorphic vector field. We want to assume that it has finite singular set. And it has what we're going to call P0, the critical singularity with the linear part, non-degenerated one. So the first thing that we observe is that the generic orbit of such a guy is C star, is periodic. Why? Well, we already know that orbits are C or C star, but beside the critical singularity, you have a lot of separatists because it's the critical, So a lot of separatists. The one leaf containing a separatrix cannot be C, because when you have the singularity, you would have C plus 1 point. This would give you a sphere, a compact one, that cannot fit into a Stein space. So all the leaves that contain separatrixes, they are periodic. They have to be C star. When you put the singularity, what you have is C. So you have a lot of leaves which are periodic, and because of Suzuki's generic orbit theory, the generic orbit is C star. So this means that most of the leaves actually are C star. Okay, so the generic orbit is periodic. So already we know by Suzuki that we have a homomorphic first integral, which is set there. Okay, so now we take a look at the singularity, P0. So the idea is to prove that singularity is analytically, the vector field is analytically linearizable in a neighborhood of the singularity. Actually, that's what happens because it's a critical. So you have Poincare-Hedoult normal form, like the book of Arnold. So either you have it linearizable, analytically linearizable, or you have the one separatrix one, which is not compatible with the existence of a homomorphic first integral. So actually, the singularities is analytically linearizable. So what happens is that you have a point, you have the critical singularity, which now has a homomorphic first integral. So it's the most critical that you can imagine. So in a neighborhood, everybody is a separatrix. In the neighborhood of the singularity, of course it takes a big word, no? So in a neighborhood of singularity, everybody is a separatrix. So you have a small neighborhood where every leaf goes to the singularity. So you can talk about the BASIN of attraction of that singular point. No? So the idea is to study this BASIN of attraction. We know that since the flow is complete, since the vector field is complete, you can extend the analytic linearization, which is defined in the neighborhood of the singularity. You can extend it by standard arguments to the BASIN of attraction. So if you want to prove that the vector field is globally linearizable in the manifold, you can study the BASIN of attraction and prove that the BASIN of attraction is the whole manifold. Okay, that's what you can prove. So if you prove that the BASIN of attraction of the critical singularity is the whole manifold, then we are done. Because at once the BASIN of attraction will be C2, because the BASIN of attraction of a linear die, and at the same time the vector field will be globally analytically linearizable. So the point to prove that the BASIN of attraction is the whole manifold is to study its boundary. So the basic steps would be, we prove that the boundary, we want to prove that the boundary actually is empty. Okay? So what we prove first is that the boundary is a union, you study how big is the boundary. So we prove that the boundary is possibly empty, or it's a union of some singularities and some analytic curves. But each analytic curve, we prove that once in the boundary, the analytic curve must go to a singularity of the vector field that we will prove to be non-decritical. So this way is a way of controlling the number of analytic curves in the boundary. So if we prove that we have the boundary consisting of analytic curves, and each analytic curve has to go to a non-decritical singularity, then we prove that the boundary is a union of a finite number of analytic curves, because non-decritical singularities have a finite number of separatrices. So if we prove that the boundary is a finite number of analytic curves, then we are done by some extension argument that we will see in a while. Okay? So after that, the extension argument somehow like you prove that the manifold, once you have proved the other step, you prove that the manifold is the boundary plus the BASIN of attraction. And as we said, since the manifold minus the boundary C2, the boundary has to be empty. So the point actually is to prove this, that the boundary is a union of non-decritical singularities and analytic curves going to non-decritical singularities. So they will be finite number. Well, so on the way of proving this, we want to study the leaves and the orbits, the leaves of the foliation induced by the vector field and the boundary. Okay, so basic things are the boundaries invariant, that's the boundary of BASIN, and it's a union of leaves and singular points. No? So the first thing to prove in order to study the boundary is just to observe that the boundary cannot contain a leaf which is closed. Every leaf in the boundary has to go to some singularity. It cannot be a closed leaf, holomorphic to C star, for example. And then we know that all leaves are holomorphic to C star. Let me explain this part. We start with generically the leaves are holomorphic to C star, but actually all the leaves are holomorphic to C star, because we know that the flow of the vector field is periodic in a neighborhood of the singularity, because we have a meromorphic first integral. So it's periodic everywhere. So if the flow is periodic everywhere, all leaves are periodic. So all orbits are holomorphic to C star. So what we are saying actually is that the boundary cannot contain a closed leaf. This means every leaf in the boundary has to go to some singularity. And the reason is quite simple after all. Let's see why the boundary cannot contain a closed leaf. There's a lot of computations there, but some computations, but the idea is very simple. Maybe just with words we can say this. Why you cannot have a closed leaf in the boundary? Now, if you have a closed leaf in the boundary, this leaf is an analytic curve itself. So what you do, you take an homology generator for the leaf. Okay? Now, we know that this leaf, we use some kind of Rib stability theory. This leaf has finite holonomy. Why? Because we have a homomorphic first integral. So you have a leaf which has finite holonomy. No? And this leaf has, you take an homology guy in the homology generator because the leaf is a cylinder. No? And then, since the holonomy is finite, suppose the holonomy is trivial, for example, no? Then you can lift this homology generator to other leaves. Okay? So using an argument, you just get the one form that generates the holonomy of this leaf, no? And then you use a simple argument. A theorem of Cartan says that when you have that's where you use that the leaf is closed. If you have an analytic curve on a Stein space, so this curve is given under the hypothesis I'm having, it's given by an equation like f equal to 0, f holomorphic map. So the theorem of Cartan says that any holomorphic one form on this curve can be extended to the Stein space. Just an extension theory. So this is where you use the fact that the leaf is supposed to be closed. This means the whole leaf is given exactly by f equal to 0. So if you get a one form that gives the homology, a holomorphic one form on the leaf, you can extend it by Cartan. So this homology is read by this one form. So you already lifted this path which generates the cylinder. You have already lifted it as a closed path to the other leaves using the finiteness of the holonomy. And then this one form will still be non-zero on these guys because of continuity. So this means that the leaves close to the boundary leaf that you are working with, they cannot be homologically trivial, and they cannot be homologically embedded in a trivial space. So after all, what happens is that you are in the boundary, imagine here, this is the leaf, and from one side you are in the basin of attraction. But in the basin of attraction, the leaves are C star, and they go to the singularity. So they are C star. When you put the singularity, they become C. So homologically they are trivial. So this gives you a contradiction. So this leaf in the boundary cannot be closed. Otherwise, everybody would have homology beside it. But those who come from the inner part of the basin of attraction, they cannot have homology because they contain in their closure the singularity. So they are C with the singularity. So no closed leaf in the boundary. Okay. So summarizing, we already know that all leaves are homomorphic to C star. So we have no closed leaf in the boundary. So every leaf in the boundary has to go to singularity. Now I will just say that the singularity cannot be the critical. This means it has to have a finite number of subparticles. Actually, if the singularity is the critical, then you do the same procedure. You consider the basin of attraction because it has a homomorphic first integral, and then you have leaves in the boundary who go to a critical singularity. And these leaves are approximated by leaves coming from the basin of attraction. So you have leaves at the basin, in the basin of attraction, that go from one singularity, which is the critical, to another singularity, which is the critical. So you have leaves that you can add one point singular and another point singular. So you have C star plus 1 point plus another point. Again, you're going to have a compact curve which cannot fit into a Stein space. So this cannot happen. So actually, the leaves in the boundary, they have to go to non-critical singularities. Very well. So this is a way of counting the number of leaves in the boundary. You have to consequently, as a consequence of that, the boundary is a union of analytic curves, because the leaves are C star, you know, that each curve accumulates a unique non-critical singularity. So this way, since the number of singularities of the vector field is finite, the boundary is made by a finite number of analytic curves. So this is enough for us to prove that the manifold is the BASIN union, the boundary of the BASIN. It's just a topology argument. You take out the manifold, of course, we are assuming to be connected. So you take out the boundary of the BASIN, and you consider the BASIN. It's the fact that you have two open sets that have a common boundary, one inside the other, then they are the same. But that's all. No? So this proves that when you take out the boundary, what you have is the BASIN of attraction. So actually the manifold is the BASIN of attraction union the boundary of the BASIN, which is there. Now to prove that the boundary of the BASIN is empty, you have some homology argument. But think about that. The BASIN is C2, and the manifold, we made the hypothesis that it's H2 of the manifold is 0. So the boundary cannot exist. So this way, the manifold is created by the boundary, which is empty, and the BASIN. So therefore, the manifold is just the BASIN of attraction. So the conclusion is the manifold is just the BASIN of attraction. Well, this implies that the vector field is globally, analytically linearizable in the manifold. Question should be, if you consider holomorphic vector field on C2, just to make it more simple, suppose you have a linearizable singularity at the origin somewhere. So the question is this guy analytically linearizable on C2? No. There are some references I would like to mention about this. There is a work by Marco Brunello where he kills the classification of polynomial vector fields which are complete on the complex plane. A former work by myself and Servo. We do partial classification. So, but this is the polynomial work. Gies and Rebelo have studied the singularities of holomorphic flows. They prove they are not so degenerated. So using the work of Gies and Rebelo, you can come back and replace the non-degeneration hypothesis I gave by no hypothesis at all. This is the outstanding work of Suzuki from the late 70s, where these two works, electron nodes, he proves what I said, the regularity of holomorphic flows. Okay, so essentially it's a very simple result, and in this question we have worked a little bit me and some of those with which I do cooperate, and we have some results, but nothing so serious. So we think that still it's a good question to think about, that local linearizability plus completeness hypothesis for holomorphic vector field may imply global linearization. So far we have no counterexample. Okay, so that's all I wanted to say. Gracias, Pepe, for being there many times, many times.
vector field with on C2 with a saddle singular point. It is a complete vector field, but with not a nodal singular point.
Yeah. We cannot solve it yet. But you consider what? A saddle point, which means non-critical with resonant eigenvalues?
Not necessarily linear.
Linear, yeah.
Linear. So it seems that it is not a case covered by your theorem.
A saddle point, which means real quotient of eigenvalues.
For instance, real negative quotient of eigenvalues.
Real negative. No, it's not covered. No, it's not the critical. So it's not the critical, it means no.
Yes,
so
but
I don't know how to.
You require that the point should be critical from the very beginning.
Yeah, for us.
So not completeness, but also the critical singular point. Yes.
Yes.
I
Since
see.
the very beginning it has to be critical. Otherwise, we cannot even start to speak about the BASIN fraction.
I see.
That's it. But the question, for example, regarding this, because this the work of Pepe Seade about non-linearizable Kramer maps, which is somehow the holonomy of such a vector field. You can make a synthesis. You can construct vector fields which are corresponding to his diffeomorphisms. So, and these vector fields are not linearizable. So the question would be if a guy like this can be embedded into a complete one. So it's a good question. We think that if you put a Pepe-Seade vector field, let's say like this, plus complete cannot exist. This means, in your case, a saddle non-resonant. If you put complete on C2, it's going to be linearizable. I think so. I don't have a proof yet.
Other questions? No, if not, we thank the speaker again. And we meet at 12.